Multimeters explained. Number 2. Continuity and resistance. In the last program, you were introduced to the basic setup, safety, and maintenance procedures for analog and digital multimeters. In this program, you will learn how to use analog and digital multimeters to check for continuity in wire, fuses, and transformers, as well as checking the bias of diodes. You'll also learn how to use both multimeters to measure resistance.
To begin, let's define continuity. Continuity is the existence of an uninterrupted current path of low resistance between 2 points. In this diagram, you can see a continuous path between point A and point B. Continuity tests are used to locate broken or burned out connections, common connections or shorts, and to check the bias of diodes. Let's set up the analog multimeter to check this wire for continuity. First, turn the function switch to the positive DC setting. Then, set the range switch to the R times 10,000 range. Although any resistance scale can be used, the R times 10,000 range often gives the best continuity reading. Next, plug the red test lead into the recessed jack labeled positive, and the black test lead into the jack labeled common. Then touch the probes together and use the 0 ohms control to align the needle on the meter face with 0 on the top scale. It's important to note that when the test leads are connected together and the top scale reads 0, the multimeter is indicating that there is an uninterrupted or continuous current path through both test leads. In other words, the circuit formed by the 2 test leads has continuity. If the needle aligns with the infinity symbol at the other end of the scale, there's no continuity in the test lead circuit. In this case, make sure that your leads are fully seated.
Let's begin to check the wire for continuity. First, connect the alligator clips to the probes. Then, touch one probe to one end of the wire and the other probe to the other end. The multimeter reads 0. This indicates that the wire offers an uninterrupted or continuous current path from point A to point B. Therefore, this wire has continuity. Let's interrupt this continuous path by cutting the wire to see how the multimeter will respond. Once the wire is cut, the current path is no longer continuous. Now the needle aligns with infinity, indicating a loss of continuity between points A and B.
The digital multimeter can also be used for continuity checks. First, locate the special scale for continuity indicated by the diode symbol. Turn the rotary switch to select that scale. Notice that the multimeter displays OL. You may remember that OL stands for overload and is displayed when the test leads are not making contact with one another. Therefore, OL indicates no continuity. The next step is to connect the test leads. Plug the red test lead into the jack labeled with the ohms symbol. Then, plug the black test lead into the jack marked COM. When you touch the 2 probes together, the digital multimeter produces an audible tone, indicating an uninterrupted current path of low resistance in the circuit. The values displayed are not important for continuity testing. Now that both multimeters are set up, let's check this fuse for continuity.
This type of fuse consists of a thin metal strip connecting the 2 contacts at either end. When you check fuses for continuity, you are actually performing a test that is almost identical to checking a wire for continuity. With the alligator clips attached to the probes, connect them to both sides of the fuse. If the fuse has continuity, the multimeter will emit a tone. This indicates that the metal strip inside is providing a continuous current path. This burned-out fuse produces an OL reading because the element cannot provide a continuous current path.
Multiple conductor cables can also be tested in a similar fashion. Remove the alligator clips and touch each pin on the connectors. The continuity check allows you to locate both ends of a conductor or to find broken conductors. All of the conductors in this cable are providing continuity from one end to the other.
Another component that can be tested for continuity is the transformer. Notice that this transformer has 2 wires on the left and 3 wires on the right. The schematic for this transformer shows that the wires on the left create one continuous path between points A and B called the primary winding. The 3 wires on the right also create one continuous path between point A, the center tap, and point B. This path is called the secondary winding. Let's use the digital multimeter to check the transformer for broken or shorted out wires in the primary and secondary windings. First, attach the spring-loaded clips and check the 2 ends of the primary winding. You should hear the tone that indicates continuity. Next, check for continuity between one end of the secondary winding and the center tap. Then, check from the center tap to the other end. Again, you should hear the continuity tone.
It's possible for a short to occur between the primary and secondary windings. To test for a short, connect one probe to one end of the primary winding and the second probe to one end of the secondary. Since this transformer is good, OL is displayed and no tone is heard.
The continuity test can also be used to check the bias of diodes. A diode allows current flow in only one direction. That direction is called forward bias. Reverse bias indicates the direction of current flow that the diode will not permit. To check the bias of a diode, connect the negative probe to the negative lead which is closest to the silver band. Then, connect the positive probe to the other lead. The multimeter emits a tone because of a continuous current path through the component. Therefore, the diode has forward bias. If you switch the probes around, you will see that the multimeter will indicate no continuity or reverse bias.
There are a few points that you should keep in mind when performing continuity checks. First, before testing for continuity, be sure that the power to the circuit is off. Second, circuits with resistors may give misleading results. Low-value resistors will provide continuity and high-value resistors will not. Third, circuits with capacitors or any other component that stores energy cannot be tested for continuity. Lastly, components connected to complex circuits, such as those on this PC board, cannot be checked for continuity without first being removed from the board.
In addition to checking for continuity, multimeters can be used to measure resistance. The unit of measure for resistance is the ohm, represented by the Greek letter omega. A kiloohm is equal to 1,000 ohms, and a megohm is equal to 1,000,000 ohms. Therefore, 75 kiloohms, or 75K, equals 75,000 ohms. 4 megohms, or 4M, equals 4,000,000 ohms.
Now, let's measure the values of these resistors using the analog multimeter. First, check that the function switch is set to the positive DC setting. Next, set the range switch to the R times 1 range. Check that the red test lead is plugged into the positive jack and that the black lead is connected to the common jack.
The top scale is used for resistance measurements. 0 ohms is at the far right end of the scale, and infinity or maximum resistance is at the far left. Notice that the resistance scale, having a maximum reading at the left, is opposite to the other scales. Then, touch the probes together and check that the needle aligns with 0. Next, using alligator clips, connect one probe to either resistor lead and then connect the other probe to the other lead.
Looking at the meter face, you'll see that the needle is on 10. To determine how many ohms the reading represents, multiply the reading 10 by the range selected, which was times 1. This gives a total measured value of 10 ohms. To check your measurement, look at the colored bands on the body of the resistor. Using the EIA color code, these bands stand for 1 and 0, with a multiplier of 1. Therefore, 10 times 1 gives a total rated value of 10 ohms. The fourth band is for tolerance, which is the allowable deviation from the specified rated value. This gold band indicates that the resistor has a tolerance of plus or minus 5%. 5% of 10 equals 0.5 ohms. Therefore, plus or minus 5% equals plus or minus 0.5 ohms. Adding 0.5 to 10 equals 10.5 ohms, and subtracting 0.5 from 10 equals 9.5 ohms. Therefore, the resistor is good, because the measured value of 10 ohms falls within the tolerance limits of 9.5 ohms to 10.5 ohms.
Let's try measuring this resistor. Connect your probes and look at the top scale to get your reading. This resistor gives a reading of 20 when set to the times 100 scale. Multiplying the reading 20 by the range selected 100 gives a total measured value of 2,000 ohms. Checking this measurement, the colored bands stand for 2 and 2 with a multiplier of 100, giving a total rated value of 2,200 ohms. The fourth band indicates 5% tolerance. 5% of 2,200 equals 110 ohms. Therefore, the tolerance limits are 2,090 to 2,310 ohms. The resistor is not good because the measured value of 2,000 ohms falls outside of these tolerance limits.
Now, let's set up the digital multimeter to measure these resistors. First, turn the function switch to off, and then to the resistance scale indicated by the Greek letter omega. Since the digital multimeter powers up in auto range, the proper resistance range will be automatically selected. If you want to manually select the range, press the range button to select the ohms, kiloohms, or megohms scale. To return to auto range, hold the range button down for 1 second. Then, check that the red test lead is plugged into the jack labeled with the ohms symbol, and that the black test lead is plugged into the jack marked COM. Next, connect one probe to the resistor lead and the other probe to the other lead.
The multimeter displays a measured value of 271.3 followed by a K, indicating kiloohms. If you check your measurement, the color bands indicate that the resistor is rated at 2 and 7 with a multiplier of 10,000, giving a total rated value of 270,000 ohms or 270 K. The fourth band indicates a tolerance of 5%. 5% of 270,000 equals 13,500 ohms. Therefore, the tolerance limits are 256,500 to 283,500 ohms. The measured value of 271.3 K, or 271,300 ohms, is within these tolerance limits, indicating that the resistor is good.
Let's try one more resistor. Connect your probes and check your reading. The multimeter indicates a value of 100.3 ohms. For simplicity, let's round off this value to 100 ohms.
Looking closely, this resistor is rated 100 ohms at 10% tolerance. 10% of 100 equals 10 ohms. Therefore, the tolerance limits are 90 to 110 ohms. The rounded off measured value of 100 ohms falls within these tolerance limits, confirming that this is a good resistor. The procedures for measuring resistors in a circuit are identical to those you've just seen. However, be sure that the power to the circuit is disconnected.
Now, let's review what you've learned in this program. Continuity is the existence of an uninterrupted current path of low resistance between 2 points.
Continuity tests are used to locate broken or burned out connections, common connections or shorts, and to check the bias of diodes.
You learned how to perform continuity tests on a number of common components. And you learned how to check the bias of diodes. You've also seen how to perform resistance measurements using both multimeters.
This completes the program on continuity and resistance measurements. In program number 3, you will learn how to measure current and voltage.